Hello everyone, this is Greg from ChemCore. Welcome back to the explainer videos. In this video, we're going to be going through the Lewis acids and bases worksheet. If you haven't had a chance to look at this worksheet or look at the answer key, it's available in the description below. And if you haven't watched the topic video for this yet, that is also available in the description below. I really suggest just to review, understand the concepts if you haven't watched that yet. Let's begin by kind of summarizing what a Lewis base and a Lewis acid is. And so what I'm going to do is, in the video I kind of explain just by words, but I also mentioned that the best way to understand what a Lewis acid and base is to remember the name of them, Lewis. You recognize this name from something else, Lewis structures. And so actually the really awesome way to understand what a Lewis acid and base is to use your Lewis structures. And so I'm just going to draw a generic kind of maybe something like this with a lone pair. And so if we have this lone pair, we can kind of donate this somewhere else. And this would define our Lewis base. Basically something that has a donatable electron pair. However, if we have something like this that doesn't have a lone pair, assuming the fact that it kind of won't break the octet rule if it grabs a lone pair, well, then this would be an acid, okay? And so we say that bases are donors, while acids are acceptors, okay? It's kind of almost the opposite of what we talked about in Bronsted-Lowry, except this time we're considering the electron pairs instead of a proton. And so the Lewis definition is really useful to describe compounds or molecules as acids and bases when they actually don't have protons that are being accepted or donated. And so it's really neat. It describes a whole kind of broad spectrum that Bronsted-Lowry wouldn't be able to describe. And so the first question is really just asking us of this concept what we just talked about, in which we define the Lewis acid as an Lewis base as an electron pair donor. Question 2 and question 3, and actually a lot of the other questions in this worksheet, is actually the exact problem where I think Lewis structures are going to be really useful. So again, let's remember that a Lewis base should be able to donate a lone pair. Since it donates a lone pair, it has to have a lone pair to donate, right, in the first place. And so a really great way to understand what is and what is not a Lewis base is to draw out the Lewis structure. And if it has a lone pair in the central atom, or the atom that's kind of, the base, then it will be a Lewis base. And if it doesn't, well, then there's no lone pair to donate. And so it's not going to be a Lewis base. And so this is where your Lewis structures becomes really useful if you're kind of struggling with that concept. I have a video on that as well. NH3, nitrogen likes 3 bonds with a lone pair. And so because of this lone pair, we know that it is a base. And so we can eliminate NH3. H minus, since hydrogen now has a minus negative formal charge, we know that it has an extra electron. And so because of that, now it has a negative formal charge, meaning that it has a full electron pair to donate, meaning that it also qualifies as a Lewis base. BF3, if we were to draw it out, remember I kind of mentioned boron as an element that a lot of questions will kind of ask you to trick you. Remember that boron looks a lot like nitrogen, kind of, except the fact that it has no lone pair. It has 3 bonds without a lone pair. And so remembering that, kind of keeping that in the back of your head, will remind you in the fact that there is no lone pair that we can donate. And so BF3 is not a Lewis base. We'll keep that open. We'll just define the rest to make sure that we're understanding everything. H2O has actually 2 lone pairs around the oxygen. And so one of these can definitely be donated, meaning that it definitely qualifies as a base. And CH3, notice that CH3 now has a negative formal charge. And remembering from our formal charges video, if we have a carbon with a negative charge, we have 3 bonds and a lone pair. And so this lone pair makes it a base. And so CH3 also can act as a Lewis base, meaning that our answer is C, BF3. In the next 2 problems, we're going to be focusing on the definition of a Lewis acid, in which we now know that we can accept a lone pair. And so again, if we can draw a Lewis structure for these and kind of devise maybe somehow that it can accept an extra electron without breaking an octet rule, well, then it qualifies as a Lewis acid. And so what can happen is, well, if H3O plus has something like this, right, where it has a positive formal charge. And so if you can kind of assume that if we eliminate one of these protons, we can then take another one of these lone pairs, well, then it accepts another lone pair, technically, and so it can act as an acid. BF3, although it wasn't a base, right? It wasn't a base because it doesn't have a lone pair as a neutral molecule. It can definitely gain a lone pair without breaking an octet rule. And so if it gains a lone pair, we end up having a negative formal charge, meaning that we definitely can act as an acid. NF3, and so if we were to draw NF3 out, we already have kind of a lone pair, meaning that we should assume that this is a base, right? And we can't we can't break any of these fluorines off and get another lone pair. Nitrogen, if we just add another lone pair without breaking a bond, we end up breaking the octet rule. It's not the same with boron. Boron, we don't have to break a bond. And so nitrogen cannot act as a Lewis acid. And so we can kind of eliminate NF3. And then hydroxide, we already have kind of 3 lone pairs on oxygen. We definitely can't break off this last proton. And so it's definitely a base, but it's not an acid, right? And so A and B are both Lewis acids, meaning that the answer should be E, more than one of these choices. And the next problem, we're considering which one of these is not a Lewis acid. And so remember, again, we're trying to look for the one that can accept a lone pair. And so let's draw all of these out. AlCl3 kind of looks a lot like boron, right? In which we have 3 bonds without a lone pair. You know, uncharged, it definitely doesn't have a lone pair, but it could get another one without breaking the octet rule, in which it'll just be negatively charged. And so this definitely could act as a Lewis acid. H3O plus, like in the last example, we have a lone pair on oxygen with a positive charge, but if we were to break off one of these protons, we definitely could get another lone pair, meaning that it also can act as an acid. FeCl3. Again, iron is kind of weird. This is not fully covalent. This is actually, we shouldn't draw a Lewis structure for this technically, but just to conceptualize it, iron is a metal. It's not a non-metal, and so what can actually happen is that it definitely could accept another lone pair. Metals are like that, so aluminum is kind of like that as well. And so iron can definitely accept another lone pair, in which it kind of just goes down in oxidation state. And so it definitely is also a Lewis acid. SO3 now should look something like this, right? Yep, six bonds. And so what can actually happen is we can definitely kind of break one of these bonds and then add an extra lone pair on sulfur. Sulfur can definitely kind of go past that octet rule. We talked about that in the Lewis structure video. And so it can also act as an acid. While C4H10, I'm going to draw this as a bond line, there's no way you can break off one of the hydrogens. Remember, carbons don't let go of hydrogen just like that. And so it will not act as an acid. Okay, and so this definitely will not act as an acid. In number 5, again, we're trying to consider the Lewis acid. And so just like in the previous problem, if we have aluminum surrounded by bromines, it's kind of a metal. It can definitely get another lone pair. It'll just be negatively charged. And so it can also act as a Lewis acid. Boron trichloride, if we were to draw this out, it has 3 lone pairs, three bonds without a lone pair. Doesn't mean it can't get an extra lone pair and just be negatively charged. And so it can definitely act as an acid. Phosphorus surrounded by these phenyl groups, which we'll talk about later. This is kind of an advanced question. And so if you're not sure what pH is, don't worry. We'll talk about it in a video in the next unit. But phosphorus already has these 3 bonds and a lone pair. And we can't just break off one of these phosphorus. It's not a hydrogen. And so because of that, it's definitely not going to act as a Lewis acid. And so we can kind of assume that it's answer C. It's definitely not E. But just to consider the last question, D, this is something that we consider in the future video, deuterium and tritium. D stands for deuterium, which is a hydrogen isotope in which it just has 2 neutrons. Doesn't mean it's literally anything different from hydrogen. I mean, it is in some ways, but in our cases, it's really not. And so deuterium, positively charged, literally just doesn't have a lone pair. And so it can definitely accept one, right? We can definitely accept a lone pair and just become deuterium negative, right? And so this could definitely act as a Lewis acid, meaning that our answer is C. In question 6, we're looking for the species that is a carbon-based Lewis acid. So just remember that a Lewis acid is going to be accepting a lone pair. And so if it can accept a lone pair, well, we need to have space for this lone pair. And so if we consider kind of this carbocation or positively charged carbon, a positively charged carbon has 3 bonds and no lone pair, right? No lone pair. Meaning that, well, we can kind of get an extra lone pair, right? We can end up with an extra lone pair. We can accept a lone pair. And then, that qualifies as an acid. Question 7, which of these is not a true statement? The first answer choice, all Lewis bases are also Bronsted-Lowry bases. It's definitely true, right? Because if you think about it, a Lewis base has to be able to donate a proton. And if it's able to donate a proton, we're assuming that it's going to be replaced by a proton later on. And so it's kind of like fits both definitions in which, yes, you can donate a proton, but at the end of the day, you're also going to be accepting. I mean, you could donate a lone pair, but at the end of the day, because of that, you're also going to be ending up accepting a proton. And because of this, Lewis bases also inherently qualify as Bronsted-Lowry bases. All Lewis acids contain hydrogen? No, it doesn't have to be true, right? Lewis acids are accepting a lone pair. There's no reason why it needs a hydrogen, right? We're not donating this hydrogen. We're accepting a lone pair. And so we actually seen examples like that earlier in this worksheet. And so if you haven't, just, wind back and see all these examples that we talked about Lewis acids, you don't need to have a hydrogen to qualify as a Lewis acid. So we'll mark this as a probable answer. All Bronsted-Lowry acids contain hydrogen. It has to be true that the inherent definition of a Bronsted-Lowry acid is that you must be able to donate a hydrogen. If you don't have a hydrogen to donate, you can't be a Bronsted-Lowry acid. All Lewis acids are electron deficient. This is a concept that we're going to kind of go into more depth later, but if you just understand what general vocabulary, what a deficiency means, deficient means you're kind of missing electrons or you're out of electrons. And so if you look back at our examples in which a molecule like boron trifluoride might not have a lone pair when it's neutral, but it could get one, right? Because of these fluorines, if you really think about it deeply, these fluorines are super electronegative, and so they're pulling all that electrons away from boron, meaning that it is electron deficient, right? And so because of that, if you're able to kind of accept a lone pair, you should be electron deficient. You know what I mean? It doesn't just go positive to positive or negative to negative. A negative has to be attracted to a positive. And so we can assume that this is also going to be true. According to the Bronsted-Lowry theory, water is both an acid and a base. This should be kind of clear to you right away. It's also, according to the Lewis definition, it's also an acid and a base. And if you're not, completely sure about that, go to the last explainer video or the last video, the topic video in which we talk about Bronsted-Lowry acids and bases, and it'll make a lot more sense to you. And so our answer should be B. In number 8, according to a Lewis definition, an acid is A. We should be very, very familiar with this by now. The definition of a Lewis acid is an electron pair acceptor. The reaction between which combination of substances can only be classified as a Lewis acid-base reaction. And so if I'm looking for the one that's only a Lewis acid-base reaction, and assuming that they're telling us, well, it's definitely not a Bronsted-Lowry acid-base reaction, I want to look for where we don't have hydrogens that are being donated. In A, we can see this kind of CH3 is kind of negatively charged, and this lithium makes it positive. We can assume that, hey, this might donate that hydrogen, and that ends up a Bronsted-Lowry acid-base reaction. So we can kind of eliminate A. I'll leave that arrow up for you guys. In the next problem, I see H2SO4, strong acid, definitely going to be donating that proton to this deficient molecule. And so we can assume this is also going to be Bronsted-Lowry acid base. Now, NH3 and BF3, if you've been going through this entire worksheet one by one with me, you should be alarm should be ringing that BF3 can kind of act as a Lewis acid, and NH3 can act as a Lewis base, in which NH3 donates that lone pair, and BF3 has electron deficiency to be able to accept it. And so I'm kind of looking at this as our probable answer choice. Now H3O plus, and I'm looking at minus, we're definitely going to want to donate one of these protons, and it ends up overall neutral, and so it's definitely going to be Bronsted-Lowry and not Lewis acid base. And so our answer is probably C. We can also eliminate E. 10 is a repetition question. I apologize. I messed up a little bit. A Lewis acid, again, it doesn't hurt to repeat. And so you should know by now, this should be drilled, or write this on your hand if something, you just remember it. I should wake you up in the middle of the night, and this should be ringing off right away, just like clockwork. A Lewis acid is definitely an electron pair acceptor. That is the definition of a Lewis acid. And another repetition question, a Lewis base is defined as an electron pair donor. Again, doesn't hurt to repeat it. BF3 is best classified as a, if you skip the questions in the past, this may seem like a new question, it's actually not. And so boron is an atom that I like to stress a lot in Unit 1, because especially during Lewis structures, when professors test on Lewis structures, they like to use boron because it has 3 bonds and no lone pair. And a lot of students confuse it with nitrogen, which has 3 bonds and a lone pair. And so because boron doesn't have a lone pair, we can consider it kind of missing electrons over here. And so, well, why can't we accept them, right? We can definitely accept some electrons. And then boron ends up as a Lewis acid. In question 13, we're looking for the compound that is not a Lewis acid. Again, let's draw them out. A Lewis acid needs to be able to accept a lone pair. And so if we were to draw BH3, we'll see that boron is kind of missing some electrons, and so we can definitely accept a lone pair, meaning that it definitely can act as an acid. AlCl3 can definitely accept another lone pair, right? Can definitely get this lone pair, and so it can also act as a Lewis acid. Now CbR4, this should kind of, right away you should kind of see this as an answer. We can't just cut off one of these bromines. It doesn't work like that. And so we can't just get a lone pair from nothing. If we get another lone pair, we're breaking the octet rule. And so it probably cannot act as a Lewis acid. And so we're going to mark this down. Now CH3CH2, right, if we have something like this, in which we have 3 hydrogens coming off this carbon, and we have a positive charge on this carbon, the positive charge means that we have 3 bonds and no lone pair, which means that we can get an extra lone pair and just turn negative, right? And so it definitely can act as a Lewis acid. And then FeBr3 can definitely, it's a metal, we can definitely get an extra lone pair and become an acid or act as an acid. And so our answer is C. And 14, which of these compounds is not a Lewis base? Remember that to qualify as a Lewis base, you need to be able to donate a lone pair. And to donate a lone pair, you kind of have to have a lone pair to donate. And so if we look at NaOH, again, this is kind of like, it's not really a Lewis structure, but remember that OH is negatively charged and that sodium is just hanging around because it's positively charged. And so because we have extra lone pairs over here, we can definitely act as Lewis bases. And so we can eliminate A. Now, B, this is another example. Remember that I'm not going to draw this out. Now, we should notice is that this O is going to be negatively charged and this potassium makes it positive. They kind of like equal each other out. It's ionic. And so because its oxygen is negatively charged, we know that we have an extra lone pair there, meaning that we can act as a Lewis base. And in C, this lithium is telling me that we have this negative carbon over here. We probably have an extra lone pair over there. And lithium is positively charged, meaning that if we have this extra lone pair on this carbon, we can donate it. And so it definitely can act as a Lewis base. And then pH3 phosphorus, if we were to draw this out, you don't know what pH is yet, but it doesn't matter because you should know phosphorus likes to form 3 bonds and can also have a lone pair. It can look a lot like nitrogen, in which if we have this lone pair, we can donate it, right? And then the last problem, we have a positively charged carbon. Remember that positively charged carbons have 3 bonds and no lone pair, meaning that if we don't have a lone pair, we don't have anything to donate, right? We don't have lone pairs to donate, meaning that it can not act as a Lewis base. And then question 15, which of the following compounds is not a Lewis acid? Again, remember that we're looking for the one that can accept a lone pair. And so let's draw these out one by one. BF3, we can definitely we don't have a lone pair here as it is, and so we can definitely accept another lone pair. And so we can definitely act as an acid. FeCl3, this is kind of getting repetitive if you've been going one by one. You should kind of understand these by now. Again, we don't have any lone pairs as it is. It's not really a Lewis structure, it's a metal. And so we can definitely accept another lone pair. This can definitely be brought here. We could definitely act as an acid. And this positively charged carbon is telling me that we have 3 bonds and no lone pair. So it's deficient in electrons. It can definitely get some extra electrons, in which it'll just turn negative. And so it can act as a Lewis acid. Now, phosphorus and then these pHs, which are, you don't know what they are yet, but remember that phosphorus has a lone pair as it is. We can't just get another lone pair. That's going to break the octet rule. And we can't just cut off any of these pHs. They're not hydrogens. And so we cannot act as a Lewis base. This is probably our answer. But let's make sure with AlBr3. Again, this is also kind of metal. Aluminum can just grab an extra electron. It's no big deal for it. It's a metal. And so our answer is D. Starting question 16, we're moving away, kind of identifying just straight from multiple choice what could or could not be a Lewis acid and base. And we're now going to practice with some reactions. So analyzing some reactions and understanding which one is our Lewis acid, which one is our Lewis base. Remember that a Lewis acid should be able to accept a lone pair. And so I kind of like to look at the end, the beginning and the end, and kind of see, okay, which one kind of ended up with an extra bond or an extra lone pair. And so if we can find something like that, well, now we know what is our Lewis acid. And the really thing that's striking me here is this iron first had 3 bonds, now it has 4 bonds. And so because of that, we kind of can assume that it accepted a lone pair in the form of a bond, right? That's just electrons. And it became negative, which makes perfect sense. And so our answer is A, right? And, the structure 1 acts as the Lewis acid, and then structure 2 acts as the base. In question 17, we're again trying to identify the Lewis acid. And so what I really notice is that boron here only had 3 bonds, while in the next structure, in the final, in the product, we now have 4 bonds. And it turns negative as well, which totally makes sense because we have an extra bond, while nitrogen becomes positive. And so because of that, we can assume that boron accepted another electron or electron pair in the form of a bond, and nitrogen gave one away. And so we can say that structure 1 is our Lewis acid. In question 18, again, we're trying to identify our Lewis acid, in which, remember, we're trying to find the one that can accept a lone pair. Now, what really kind of I understand is that this oxygen ends up becoming neutrally charged, which means it becomes more negative, right? If it went from positive to neutral, it's going like going from positive 1 to 0, you got to subtract something, right? Or add a negative. And so because of that, we're assuming that we gained some more electrons, maybe in the form of a bond or in the form of just electron pairs, meaning that we accepted electrons, and so structure 1 is our Lewis acid. In question 19, we're again trying to identify the Lewis acid. I like to look for the one that kind of accepted another bond. And so what I notice is that this nitrogen, right over here, just had 2 bonds on each side to oxygen, while in the next structure, we kind of got another bond, right? We gained some more electrons. Some electrons were drawn to nitrogen. And so the other thing that I really like to notice is that nitrogen kind of was deficient at first, which means it was able to accept some electrons. And so structure 2 is our Lewis acid. In question 20, a good change of pace, we're looking for the Lewis base. In this case, we're looking for the one that can donate electrons. And so this is actually a reaction that we looked at earlier, in which we identified the Lewis acid. You should notice that boron becomes negative, which is kind of like you're assuming that it gains some electrons, right? If you gain negatives, you become negative. And so if we can assume that structure 1 acted as the base, as the acid, we can then identify structure 2 as our base. Question 21 is a similar question in which we're again looking for the Lewis base. We actually looked at this reaction before, in which iron became negative, which means we're accepting electrons, right? And so if we accepted electrons here, we can say that this one was the acid, which means structure 2 must be the base. In question 22, we're looking for a reaction, but this time we're identifying both the Lewis acid and Lewis base. And the trick I like to do is I like to notice that, well, aluminum became negative, which means we probably accepted electrons. And according to our definition, structure 2 must have been the acid. While this chlorine kind of became positive, which means we donated electrons. And if we donate electrons, that fits our definition of a Lewis base. And so structure 1 should be our base, and structure 2 should be our acid. In question 23, we're again identifying the Lewis acid and Lewis base. I like to notice at first that this positive became neutral, right? And so if we go from positive to neutral, that means you became kind of more negative, in which case we gained electrons, so we accepted electrons, which fits our definition for a Lewis acid. While nitrogen became positive, which means we can assume that we donated electrons, which fits our definition of a Lewis base. And so the answer choice that fits this is B. Structure 1 is our Lewis acid, structure 2 is our Lewis base. To summarize, we're going to wrap up with defining, again, kind of some interesting things about Lewis theory. So according to Lewis theory, a base is a substance that can donate a pair of electrons. And 25 is kind of repeating this concept. A substance that can donate a lone pair of electrons is a base according to Lewis theory. These two questions conclude the explainer or the worksheet for Lewis acid-base theory. If you're unfamiliar with these concepts, I really suggest to go check out the topic video, which is linked in the description below. And if you want to retry this worksheet or look at the answer key, they're always available for completely free in the description below. I'll see you guys in the next video.